So we have the differential equation, f prime of x, same as having a dy dx, right, is equal to e to the negative x squared. And we want to find f of x for which f of 7 is equal to 3. Now, I am going to tell you right off the bat that I am 100% positive that none of you know what the integral of e to the negative x squared is. Would you all agree with that?
Yes.
Yeah, definitely not, because the that function is not really integrable. You can't actually find an explicit function that has a derivative of e to the negative x squared. I mean, that's an oversimplification, because there is such a thing that allows you to sort of take the antiderivative of this, but in reality, there is no basic function that has a derivative of e to the negative x squared. But we should still be able to come up with a solution to this differential equation. It'll just involve an integral in it. And we're going to be able to use this information to still be able to figure out the appropriate constant. So if we don't actually know the integral of e to the negative x squared, couldn't we just call it an integral of e to the negative x squared? Dx?
Sure.
I mean, that's what it is, right? I mean, that's definitely what it is. Now, we always have to add a constant to it, right? And this develops just a small amount of a problem here, because this is not really very helpful. We want a specific function where we actually have the constant. And so we're going to use this information here to develop a lower limit and an upper limit for this function, so that if we plugged it in, we would be able to find out what that constant is. And so normally when we did all of these integrals and we went from an integral of something from a lower limit to an upper limit, and back when we were doing the fundamental theorem of calculus, oh my gosh, what happened to my stuff? Oh no. Oh man. I got it back. Don't worry. Normally, that's not what I wanted to do either. Having some trouble here. Normally, we used a different variable here, right? Normally, we had like a t here, e to the negative t squared dt. And how did we turn that when we did the integral and the derivative and all that? How did we turn that into x? We put a constant down here, didn't we? Let's call that constant 1 and call that constant 2. And then we put an x up here. And if we were to take the derivative of this thing that I now have here, would you agree that we would get e to the negative x squared, because we'd plug in the x for the t? This constant would go away. And that was our rule, was that the derivative of the integral from a constant to x of a function is just that function. Yeah or no?
Yeah.
Okay. So what is f of 7 then? What would I do with f of 7? How would I rewrite this whole integral expression that I have? Everywhere that I see an x, I should replace it with a
seven.
So this would become the integral from constant 1 to 7 of e to the negative t squared dt plus some other constant. All right. Well, we know that this, when x is 7, needs to equal what?
3.
3. Okay. So now what we need to do is we need to come up with a value for constant 1 and a value for constant 2 that make this thing true. Okay. And that's a little bit of an issue, because if I want to integrate e to the negative t squared, we already said that this integral doesn't exist. So there is only then one way for me to get an actual numeric value out of that expression. And how can I get a numeric value out of that expression? Anybody see the one and only one possible way that I can do that? Think back to your rules for integrals, not the like, not the like power rule and the rule for integrating cosine, but those like basic rules I gave you where like you could pull a constant out and you could separate it into two different ones if you had addition of the integral and all those rules. And like the integral from a to b plus the integral from b to c is equal to the integral from a to c. Remember all those rules?
Yeah.
Yeah, okay. So think back to those rules and think about a value for constant 1 that would make it possible for me to get an actual number out of this integral, even though I don't know what the function is that I would get if I integrated e to the negative t squared.
Zero.
Okay, so if constant 1 was 0, I'd have an integral from 0 to 7. So I'd have to find the function then and evaluate that function from 7 or at 7 and evaluate that function at 0. But I don't know that function, right? So I have to be able to evaluate this expression without actually knowing what that integral is. So what we need to do is find C1 so that I can evaluate the integral without integrating. That's what we need. There's only one number that I could put there that makes it possible for me to evaluate that integral without actually integrating it.
Could you switch the limits and make it negative?
I mean, we could do that, but that's not going to, I mean, that's not a value for C1. We don't need to do anything to it. There's just one number that I can put in for C1 that will make it work. Nothing needs to be done to this other than you need to tell me a number that C1 can be so that I know what this integral equals.
7.
Why 7?
Because of the rule with the same upper and lower limits. It's just
Right.
the expression in the integral.
Exactly. If we integrate from 7 to 7 of any function, what do we get?
0.
We get 0, right? So if constant 1 was 7, then that would allow me to know that this integral's value was 0, and that would allow me to tell you that constant 2 then must be what? If 0 plus constant 2 equals 3, what
3.
must constant 2 be?
3.
Must be 3. So effectively what we're doing here is we're saying that f of x needs to equal the integral from 7 to x of e to the negative t squared dt plus 3. And that is a good solution to this differential equation since we can't actually find the integral of that function. Does that make sense or no?
And so to solve this, you would just use the integral function on your calculator?
Exactly, because that integral function just uses one of the approximation methods. And you wouldn't have to, you don't have to use the calculator because we have a bunch of approximation methods, right? We could use a rectangular approximation or a trapezoidal approximation to approximate this integral and get a very close answer to what it should be, but your calculator will do it more quickly. And questions similar to this generally pop up in the multiple choice on the calculator section of the AP test. There's usually like one of the 15 multiple choice calculator questions that are like this, and they'll actually ask you to be like, oh, all right, what's f of 2? And then you'll use your calculator to evaluate it. And so we're going to do a few of those, and you're going to have a homework assignment on this specific thing tonight. But almost every year there's one of those. And so I want to make sure we're good with that. So let's look at another one. This one's a little different. This one we want to actually find the value of f of 2, given this derivative, f prime is x to the 4th sine x, and knowing that f of 3 is equal to 5. So we first want to set it up as saying f of x is equal to the integral of t to the 4th sine t dt plus a constant. And we're going to integrate this from some number to x. And we can really pick any constant that we want down here, but we want to pick the one that will strategically work when we look for f of 3. So when I look for f of 3, this x value is going to be 3, right? Up in the upper limit.
Yep.
Yeah. And so in order to then know what the value of this integral is, what do I need the lower limit also to be?
3.
3. And so this will be our initial setup. And so then we will say something like, well, f of 3, which is 5, should be equal to the integral from 3 to 3 of t to the 4th sine t dt plus our constant. And that tells us that the constant is
5.
5. And so we would then say f of x should be equal to the integral from 3 to x of t to the 4th sine t dt plus 5. And if we were looking for f of 2, which is what it asked us for, what's f of 2? It's just the integral from 3 to 2 of t to the 4th sine t dt plus 5. And your calculator will be able to tell you a very good approximation for that. And so that's what I'd like you to now do, is have your calculator find the value of the integral from 3 to 2 of t to the 4th sine t dt plus 5 after the integral. And when you type it into your calculator, you'll just make these t's x's. All right, so that's what you're going to do. Grab your graphing calculator and tell me what that value is.
Negative 19.988.
Negative 19.988. All right, other people agree with that? I haven't actually done it, so I'll make sure that's right.
Whoops.
You're sure your calculator is in radians, yeah?
Wait, I forgot to add the plus 5, I think.
So if you add the plus 5, negative 14.988.
Yep.
Other people agree there?
Yeah.
All right. Yeah, just make sure that your calculator is in radians, because there's a trig function in it. Otherwise, you're going to get the wrong answer. Any questions on that? It's kind of a cool little trick that you need an approximation method for, but it works out real nicely for some integrals that you might not be able to integrate. Now, this integral right here, that one is an integral that you actually could be able to find. You guys wouldn't be able to, but when you take another calc class, Calc 2, you learn how to find the integral of stuff like that. But any questions on that? All right. So I would like you guys to make an attempt at finding this one on your own. So I'll give you 2 minutes, 3 minutes or so to write the equation for f of x and then find f of 2. So you got 2 minutes to do that. Ready, go. First off, since you didn't know how to integrate 1 over natural log of x, you hopefully wrote this as an integral from, f of x is equal to an integral from somewhere to somewhere, right? We'll say somewhere to x of 1 over ln t dt plus some constant. And since we knew that we were going to plug in 9 as our x value, we knew that our lower limit needed to be 9. And that ends up giving us zero here, plus our constant, which needs to equal 5. So 0 plus c is 5, telling us that c is 5. So hopefully you all came up with f of x is equal to the integral from 9 to x of 1 over ln t dt plus 5. Yeah?
Yeah.
And then you put in 2. F of 2 is 9, integral 9 to 2, 1 over ln t dt plus 5. And what did you get?
.324.
0.324. Everybody agree with that?
Yes.
Cool. All right. So you will definitely have a homework assignment with a few of these to practice today. So plan on that. And then I may give you a little bit more stuff to finish up over the weekend with the rest of what we're doing. In fact, I definitely will. But you'll have this type of problem due tonight. All right. So let's move on and do a couple of motion type problems. So we're going to be given a velocity function. So the velocity of a particle is v of t is 2t cubed plus 3t squared. And we want to know the position of the particle at t equals 3 if x of 2 is equal to 1. So if we're given a velocity function, how do you think we get a position function?
Take the integral of it.
Yep. So right, derivative of position is velocity, so the integral of velocity is position. So we'll say that x of t is equal to the integral of v of t dt. And what is the integral of v of t?
One half t to the power 4 plus t to the power of 3.
Plus
C.
plus some constant, right? And
Yeah.
so that's our x of t function, but we know that x of 2 is equal to 1. So we'll say x of 2, which would be 1/2 of 2 to the 4th plus 2 to the 3rd plus a constant needs to equal 1. And so that will allow us, using this simple initial value type stuff that we were doing yesterday, it will allow us to figure out the value of that constant. So 2 to the 4th is what, 16, right? Divided by 2 is 8. So we got 8 and 8. 16 plus c equals 1. So what's our constant?
-15.
It'd be -15, which now tells us the exact position function. X of t should be equal to 1/2 t to the 4th plus t cubed minus 15. And if we want to find, what did we want to find? The position of the particle at t equals 3, that'd be x of 3. So we'll plug that in. That'd be 1/2 of 3 to the 4th, which is 81, plus 3 cubed, which is 27, minus 15. So that's 81/2 plus 27 minus 15, or 81/2 plus 12, which gives us what, 105 over 2. Good or no?
Good.
Cool. Easy enough. Same thing as what we were doing yesterday, except now we're evaluating the function just like we just were a minute ago, right, with the calculator. Now we're evaluating it by hand, but still using this initial value type stuff and incorporating the motion into it. Let's do another one. So if a of t is sine t and v prime is 3, or v of pi is 3, we want to find v of pi over 3. So I will give you guys a second to try and work this one on your own. Sound good?
Yep.
All right, cool. Ready, go. So we've got a of t is sine t, which means that v of t should be the integral of a of t dt, which is what?
Negative cosine t plus c.
Negative cosine t plus c. And if we want v of pi to equal 3, we'll just say that negative cosine of pi plus a constant needs to equal 3. And what's the cosine of pi?
-1.
Yep. And so negative 1 should be 1 plus c equals 3, giving us a constant of 2. And that gives us v of t is now equal to negative cosine t plus 2. And so v of pi over 3 ought to be negative cosine pi over 3 plus 2. And the cosine of pi over 3 is a half, so that's negative a half plus 2, or 3 halves. Good or no?
Good.
Anybody not get 3 halves? Anybody have any issues with that? All right, let's do another one. So this one, which I'm going to let you work through on your own also, is asking you to go from acceleration all the way to position, while giving you a couple of pieces of information, one about velocity and one about position. So what do you think you're going to need to do with this one?
Find the equation for velocity and then take the integral of that for position.
Exactly. So first we'll integrate the acceleration to get velocity and use the initial condition there to find the constant in the velocity function. Then we'll integrate again and have to find a new constant for the position function and then evaluate. So I have faith that you will all be able to do that if I give you 2 or 3 minutes. So ready, go. So first off, to find the velocity function, we integrate the acceleration function. And the integral of 3t squared is t cubed. Integral of t is t squared over 2. And the integral of 1 is t. And then we get plus a constant. And since we know that v of 2 is equal to 9, we can then say that 2 cubed plus 2 squared over 2 plus 2 plus c is equal to 9. So that's what I was saying, is we'll first use this to figure out what that c is. And then we won't have to worry about a constant times x when we integrate it a second time. It'll just be whatever the actual constant is. Does that make sense now?
Yeah.
Okay, cool. So this is 8 plus 2 plus 2. That's 12 plus c equals 9. So what is our c value?
-3.
-3. All right, so we've now got v of t is t cubed plus t squared over 2 plus t minus 3. And now we want to find our position function. So x of t will be the integral of v of t dt. And that integral ought to be t to the 4th over 4. And then plus t to the 3rd over 6. And plus t to the 2nd over 2 minus 3t plus some other constant. And so this time I'll just call this C1, just so that I don't have another of the exact same variable up there. And so now we know that when we plug in 1, we ought to get 6. So that tells us that 1/4 plus 1/6 plus 1/2 minus 3 plus that constant needs to equal 6. And so what did you get for that constant? Should be 9 minus a half minus a sixth minus a fourth, right? So what did that come out to be? Anybody? Anybody got that constant?
Got 97 over 12.
97 over 12. That sounds good to me. And a fourth plus a sixth plus a 12th is 11 twelfths. So it's 9 minus 11 twelfths, or 108 twelfths minus 11 twelfths, 97 twelfths. Sounds great. So we now have an x of t function. So x of t is t to the fourth over 4 plus t to the third over 6 plus t to the second over 2 minus 3t plus 97 twelfths. Not the nicest looking thing there, but that's okay. And so we want x of 2. 2 to the fourth is 16 over 4 should be 4 plus 8/6, or we'll write it as 4/3 for now. Plus this one is just 2, and then minus 6, and then plus 97 twelfths. So the 4 plus the 2 is 6, minus the 6 cancels out. So really we've just got 4/3 plus 97 twelfths. And 4/3, if we put that into twelfths, would be 16 twelfths. So what's 97 plus 16? Seems like that ought to be 113 twelfths. So it's at a position of 113 over 12 at t equals 2. Any questions on that? A little bit of work, but I hope nothing too complicated, maybe except for the arithmetic, maybe. Everybody good with that or no?
Yep.
Wonderful. That's great. So we've now done initial conditions with functions we can integrate, initial conditions with functions we can't integrate, and we have to use a calculator to approximate them. And we've done some of these initial value problems using basic motion. So hopefully now we should be able to do any of the motion type problems, whether we're going from position to velocity to acceleration or back the other direction. We should be able to go in any order we want as long as we have some conditions given to us. Anybody have any questions on any of that so far before we move into what we're going to do next? As we're going to sort of change gears. We're still dealing with differential equations, but in a completely different way. No questions on any of that? Everybody's good? All right. So now what we're going to do is we're going to take a look at some differential equations, and we're going to construct what are called slope fields. Okay? And a slope field is just an approximation of what the solution to a differential equation looks like. And we're going to start it off with some functions that we could easily integrate and know what it should look like. For example, we're going to start with dy dx equals cosine x. We know what the integral of that is, right? What's the integral of that?
Sine.
Sine. So when I construct this slope field using this differential equation, what I end up putting in here ought to look like a sine function in some form or another. Okay? But then we're going to take this idea of slope fields and not only apply it to functions that we can integrate, but we're going to apply it to functions that we may not be able to integrate, similar to like e to the negative x squared, we could see what the integral of that looks like, even if we don't have an actual function for it. Or we're going to do it with differential equations that involve more than one variable. Okay? So that's going to be our goal with these slope fields. So we're going to start with a nice easy one just to get the idea of what we're doing and understand sort of what it is. So what does dy dx represent? It's a
Derivative.
derivative. And what's a derivative?
The instantaneous rate of change.
The instantaneous rate of change. And what is the simplest word, singular word, that we can use to represent an instantaneous rate of change of something?
Slope.
Slope, exactly. And so that's what this is. This differential equation gives us the slope of the integral of this derivative, right? It gives us the slope of the original function. Cosine x is equal to the slope of y, right? Happens to be the slope of y equals sine x at any point, but it's the slope of the solution, and in fact, I'll write y equals sine x, which is a solution to the differential equation, right? That's what a differential equation is. It's just the slope. Okay. So what we're going to do is we're going to take a bunch of points in the plane, and we're going to evaluate our differential equation at each of those points. And at each of those points, we're just going to draw a little tiny line segment that has a slope of what we get when we plug that point into our differential equation. And that should represent the slope of the solution to the differential equation at that exact point. And what its slope is at that point for the function that has this as its derivative and goes through that point. So hopefully that makes sense. If not completely, I think it will by the time we're done with this first one. So what's a really easy point that we could use to plug in into our differential equation? Pick any point in the plane.
0.
0. That's not a point. That's a number.
0, 1.
0, 1. Okay. So if I'm going to use, and I'm going to just make a point there. There's the point 0, 1. If I plug that point into dy dx, so what does dy dx equal at the point 0, 1? Well, it equals the cosine of the x value, right? The y value, in fact, doesn't actually matter. It just equals the cosine of 0, which is
1.
1. In fact, at any of the points that lie on the y-axis where x is 0, what does the differential equation equal? Should always equal
1.
1. So what we're going to do is anywhere where x is 0, because x equaling 0 gives us 1, we're just going to draw a tiny little line segment that has a slope of 1. Does your slope of 1 need to be perfect? No. It just needs to be pretty much 1. Right? And those are about 1. I hope you'd agree that those all look like they're about a slope of 1. Yeah? Okay. Cool. Well, let's say this next value here is pi over 2. And so what is the value of dy dx when x is pi over 2? Should be the
0.
cosine of pi over 2, no matter what y is, right? Doesn't matter how far down or how far up I go. We should still get the cosine of pi over 2, which is what?
0.
0. So now everywhere where x is equal to pi over 2, no matter what y is, because y doesn't matter because there's no y in my differential equation, I should get a slope of 0. Agreed? And obviously there's an infinite number of these. I could draw these in, at every little point in here. but I'm just sketching a few of them just to get a general idea. All right. What about the next value? The next value would be at pi, right? What's the cosine of pi?
-1.
-1. So each of these should be -1. And what about the next value? At 3 pi over 2, what's it going to be?
0.
0. So they're all going to look like these flat little lines with a slope of 0 again. And what about when I get out here to 2 pi?
1.
They're going to go back to 1, right? And what about at negative pi over 2?
0.
0. And what about at negative pi?
-1.
-1. And what about negative 3 pi over 2?
0.
And at negative 2 pi?
1.
And looking at that slope field, you might notice that pick any point. For example, let's pick the point 0, 1 that we chose before to start with. Well, at that point, the solution to this differential equation is going up to a slope of about 1. But then by the time it gets to here, it has narrowed out. So that means that that slope is decreasing and it gets to 0. And then at 0, it starts decreasing again and goes back down to -1. So it starts to look something like this, doesn't it? It goes up, flattens out, goes down, flattens out, goes up, flattens out, goes down, flattens out, and so on infinitely. No matter what point I choose, suppose I chose, I don't know, this point right here, what does it do? It goes down, flattens out, goes up this way, flattens out, goes down, flattens out, goes up, flattens out, goes down, and so on. And what do these look like?
Sine graphs.
They look exactly like sine graphs, where at 0, it's at its equilibrium point, right? It's right in the middle, right? It's at the line that we're oscillating on. It goes up, goes back down, passes below this point, goes back up, passes back down. Looks like a sine curve. Okay? And so that's the whole point of this slope field. We can take the differential equation, we can evaluate it at every point that we feel like in the plane, and then we can sketch a solution curve that goes through whatever point we're interested in and say, all right, well, at the point, whatever this point is, 0, 1 or 0, 1/2 or whatever we want to call it, it sure looks like a very nice sine curve. And so we would take a guess that the solution to this differential equation is sine, and we know that it is, but that's what it should look like. Isn't that kind of cool?
So the y is irrelevant.
In this particular differential equation, yes, the y is irrelevant because there is no y value in this differential equation. But we will do some where the y value is relevant, where we have both an x and a y over here. Doesn't look like we'll get to those ones today. We'll get to those ones probably tomorrow. Maybe we will today. We'll see. But does that make sense?
Yeah, it does.
Okay.
Yeah, thank you.
Cool. And the reason why in this case the y value is irrelevant, we know that a solution to this differential equation is sine x, right? But it could also be sine x plus 1 or sine x plus 7 or sine x minus 1,000. It still looks like a sine curve, even if it's been shifted down 1,000 units or up pi units or down 8 units or what have you. All right. So here we have dy dx equals the square root of x squared minus x plus 1. So what we're going to do is we're going to pick some points in our plane and see if we can sketch this curve or the solution curve to this differential equation. Anybody know what the integral of x or square root of x squared minus x plus 1 is? Probably not. I'm assuming not. Yeah, okay, didn't think so. It is something that could be integrated, but since we don't know what it is, we're going to have to just sketch this solution curve. So let's pick some points. Anybody have a particular point they want to choose? Where are we going to start? How about 0, 0?
Perfect.
All right. Now, once again, for this one, are there any y values? No, there are no y values in our differential equation, so the y values aren't going to affect it again. So all we care about is the x values. So if x equals 0, what does dy dx equal?
One.
1.
Should be 1, right? Slope of 1. 1. That doesn't look very good. Let me use a different color. 1. 1. I'm just going to draw a bunch of them when x is 0. What about when x is 1? What does dy dx equal?
1.
Oh, 1, right? So, oh, didn't mean to do that. Still 1. So 1. And we might find that if we chose something in between there, let's say, what about if x was a half? We'd have something that's a little bit less than 1, wouldn't we? A half minus a fourth. Oh, sorry, we'd have something a little bit more than 1, right? A fourth, yeah, sorry, a little less than 1. A fourth minus a half plus 1 is 3/4. So the square root of 3/4 is going to be a little bit less than 1 is. So we know that between 0 and 1, it's flattening out a little bit and then increasing back to 1. But let's continue moving to the right. So what about at x equals 2?
Root 3.
The square root of 3. Square root of 3 is more than 1, right? So each of these should be a little bit steeper. And what about at x equals 3, let's say?
Root 8.
Root what?
7.
Yeah, there we go. Okay, so still getting larger. And so what's going to keep happening as we go out here further and further and further away from x equals 0? If I plug in 4, this number is just going to get bigger, right? And 5, it's just going to get bigger. And 6, it's just going to get bigger. And 1,000, it's just going to be really big. True? So this is just going to keep getting steeper and steeper and steeper. What about if we go to the left? What if x is -1? What's dy dx?
3.
Root 3, right? So a little bit steeper than each of those was. And what about if x is -2? Should be root
7.
7. And what about when x is -3? It's just going to keep getting bigger, right? So these are just going to keep getting steeper and steeper. I know my lines aren't perfect, and this is not always going to be a perfect science, but these are just going to keep getting steeper as they go towards the left. So if I wanted to pick the point 0, 0 and sketch the curve that went through that, it'd be about a slope of 1. And like we said, between 0 and 1, it flattened out a little, but then increased back up to 1 and then got really steep. And then same thing going this way, it gets really steep. And so we just get this sort of steepening, or this curve that kind of gets a little bit less steep as it goes to between 0 and 1, and then starts increasing again very rapidly after that. Does that make sense? We could pick any point on here if we wanted to, like let's say this point. and it should flatten out a little, then go back to 1, then get very steep. Good or no?
Good.
All right. Cool. That's the basic idea of slope field. We're going to actually stop right there. I don't want to get into the slope fields that have multiple variables, since the next one's probably going to take us more than 7 or 8 minutes like we have right now. So we'll stop there. We'll call it good for today. Any questions on anything we've done so far today? That was enough for somebody. Somebody left. All right.